I'm plumbing. I'm back on the 64K memory module. Um, I literally have not looked at or touched this. Well, okay, not anymore. Um, Before doing this little bit here, I had literally not touched this since I'd uploaded the video about this module. Um, Obviously, you can probably guess that doing all this kind of wore out my patience a little bit, just a little bit. And I thought, well, I'd go away, do some other stuff, and come back to it. And that's what I've done now. So I haven't done a great deal to it yet. Um, all I've done for the moment is to basically sort out these wires here. So these are the chip select pin signals for each of these Cypress SRAM chips, and I've got more of them on this piece of anti-static foam. I've got quite a few. I found a decent deal on this lot on eBay. Haven't tested them though, so but I think that might make an interesting thing to do. I thought that I might be able to cobble together something out of the parts that I've got, but unfortunately not quite. Because I've got some of these ZIF zero insertion force sockets, which are great for exactly this type of thing, because you can just drop the chip in. Oh wow, look at that, it's the exact number of pins and all. I literally just picked these up because I saw a decent price on them. Pop the chip in, push the lever down, and now that's nice and secure. And I was thinking about perhaps building one of these into an Arduino shield, and I've got some shield perf boards over there that I can't reach to at the moment. Can't reach at the moment. But it occurred to me that they are only for the sort of original Arduinos, which do not have nearly enough I/O to be able to fully do that and test these. And I don't have enough room on the shield boards to put in a bunch of shift registers. Well, I don't know actually. I may have room, but I think what I'll do is you out of focus. You are always out of focus, aren't you? There we go. But I think what I might do is have a look for some Arduino Mega sized shields, the perf board shields that would be more appropriate. Just hook up all of these pins to Arduino Mega pins and do some test routines. I think that would probably be a worthwhile thing to do, because I was a little bit concerned, and I may still be a little bit concerned about this module, because I did write a test routine. If I just unlock my computer because the screen saver has come on, I did write a test routine, and I was seeing errors coming up in it. It was like, oh no, it's not reading back the same value that it put in, and it was like, oh dear, maybe there's something up with this. And it would mightily suck, because there's going to be no way of testing these chips individually without yanking all these wires out. So let's hope that that's not a problem. Now, I already started doing writing the test routine for this and having a go with it. So I've got most things there, but I'm just going to have a bit of a play around with this and take you along for the journey. It's been long enough since I posted another Plum video. I do have another video lined up to publish, but it's not a Plum video. It's a screencast. And in the course of really getting my teeth back into this, I discovered something quite annoying in the Ubuntu 18.04 LTS release, which I've now discovered how to fix. I'm still not entirely, well, I say not entirely certain. I still don't really know what the problem is, because it involves a part of Linux that I am not really that familiar with yet, the PAM authentication system. But I found the fix, so I might do a screencast for that, because it was really annoying. So, where are we here? What are we doing? Okay. So I've put in a couple of these little register chips. These are MC74HC574Ns, and the more eagle-eyed, astute viewers would possibly notice that all these chips are backwards. Now, yes, they are backwards, which is to say that the little notch is over here on this side, not on this side. And it's the same for this as well. This the notch is here, not over there. Now that typically is an invitation for pain, and I find myself quite often wanting to put these 74HC138 3-bit 8-line decoders this way round, because in my mind a 3-bit word comes in from the top and the selections go out the bottom, which is generally how I'm laying out my boards, but all the outputs are on the top row of the chip, not the bottom, so I generally flip these around. And as a result, I have burnt through a couple of these to the point where I really wish I could see heat. And, you know, I suppose I can, it's just it doesn't get hot enough for that, which is probably for the best. But the most remarkable thing is that the electrons haven't fallen out, which they normally do. If you put the chips the wrong way around, all the electrons will fall out, and the pixies won't know which way they're dancing. But it does work if you keep your eye on what you're doing. And it turns out to be the same deal for these as well, because these are the variety of 8-bit register chip that has all of the inputs on one side and all of the outputs on the other, which is mighty convenient. The other variant that I have, is that this one? 574? No, that's it's the same kind. But I just can't remember the code for them. 273s, I think. This is the one. Is that right? Let's just have a quick look. 74273. Yes, this is the one I was thinking of. This is the one where all the pins are interspersed with each other. So there's an output, an input, an input, an output, an output, an input, an input, an output. And that makes the wiring quite annoying. So having the inputs and outputs all on the same sides for each other, you know, it basically means that the data can just sort of pass through it like that. But again, the inputs are on this side, the left. That's it, the left-hand side, and the outputs are on the right. So that meant that I had to put the chips in backwards. I have my Plum Arduino sketch that I run on here, and it acts like a sort of bit of development scaffolding / monitor ROM type deal. Let's open that up and see what I've written for memory tests. So let's have a look, see if I can remind myself where it is. cmd memory.cpp. There we go. So these are my memory commands, and I've implemented a memory test command. And if we come down to memory test, here it is. So for every address that we should be able to access in a 16-bit address bus, we go over all of them, and first off we're going to write all zeros in that location. So we select that address, and this is just a bit of abstraction for how I'm doing the memory selection. So at the moment what it'll be is I'll just define some pins here as address bus output, and it'll just put the address straight onto here, pass through here and into the chips. But another configuration that I have had previously is where it would put the address into 2 of Plum's register modules. But I'm not doing that at the moment, so just select address, the right address. Data bus out, right byte, which is zeros. And then we're going to pulse the memory in pin low, very, very quickly, because otherwise it's going to take forever to run through all these addresses. Then we can say, all right, we're done pulsing the mem in. Now we want to bring mem out low and read what's on the data bus. And looking at this, let's just check, because I think I may have been getting a false positive, false negative, whatever, false results on my test. Because if this is not releasing the data bus, then okay, let's just go and have a look at data bus and see what we've got. So data bus, there it is. Data bus acquire states. Okay, so we've got my functions for releasing the data bus, which is just set all the pin modes back to input so they become well, they're not driven one way or the other. I've got my data bus out, which is the function that we were calling. And what that will do is it will go and set all of the pins to outputs and then output the value on those pins. Data bus in. So I think yeah, I'm not very clever sometimes. So what I need to do here is data bus out, the right byte, pulse low fast. I think that's a 1 millisecond pulse. Then I'm going to want data bus release. Right, so now Plum is not driving the data bus anymore. So when we come to do data bus in, it should be what is actually coming back from the chips and not what it was still driving itself. So that probably didn't make a great deal of sense, but I do apologize if that's the case. I'm kind of winging this. I told somebody that my next video would be a Plum one, and the next one that I've got in the queue is not a Plum one, so I'm having to improvise this one for you. But you know, it's forcing me to get back into it, so that's cool. I have no problem with that. Right, so we select the address, we put the byte that we want to write into memory on the data bus. We tell the memory to read what's in the data bus and store it at the address that is being presented. We then tell Plum to release the data bus. Okay, so as far as it's concerned, the data bus is now floating again. We're now going to say, memory, please output what you're storing at this address, and we'll read it in. And then once we're done that, we can say, you no longer need to output. And we just check to see if the byte that we read is the same or not the same as the byte that we wrote. And we can print out some information about, you know, what actually happened. So this was the byte that we tried to read, colon, this is the byte that we tried to write, colon, the byte that we actually got back, and then a space, and we set a fail flag because it's failed. That we then try and write all ones, and we need to do the same thing again. So select the address, output the value on the data bus, data bus release, and that doesn't go there, but instead that goes there. And then we read it in again, and we do the same thing again. And if it has failed, we can print out the address that failed and put a new line. So this should only output addresses that have problems. Yeah, because I'm not printing out anything else. Sorry, I wrote this quite hastily last Friday, Thursday, and I'm trying to remind myself of what I've done. So, okay, that's cool. That should work, right? I mean, this was my other memory test routine that I wrote a little while back, and it was good. It was a bit of fun, but I just wanted something that would scan through the whole address space and test it. So let's hook up some wires. So tab new pins.h, because I can't remember what pins anything's on. And Yeah, they're a little bit all over the place, but whatever. We can deal with that. I get my fancy braided wires, and let's hook up some signals. So, oh, what have I got here already? Okay, these are all just kind of all over the place, so let's just pull that out. Right. So, what were those? Okay, memory address register, low clock and high clock. So these are the signals that tell these chips whatever is being presented to you, clock it in and store it, and then present it to the RAM chips. So yes, we do want those. And these pins are these ones here, right on the end. So the low byte pin I have assigned to pin 6, which is, can you see that? Yes, you can, which is here. The high byte I have assigned to pin 7. I'll use a shorter wire for that because I don't need so much length. Put that in there. So, pin mem in and pin mem out. Right. So, mem in and mem out are going to refer to these yellow signals that are being propagated to all of the chips. So there's one just under those white, there's one there, there's one on the diagonal, there's one, there's one, there's one. They go all around. Essentially, this one is write enable, and this one is output enable. So let's just pop some wires in over here, because that'll do. So write enable is mem in, which is 4. That one. And we can see that that signal is currently being asserted high because I've got this little LED in. And output enable, which is that one, goes to 5, which is there. Okay, so none of this RAM should be outputting or trying to write. So let's hook up some addresses. The lowest nibble is going to go to where? That's these 4. So A15 through 12. So those are here, and there they are, and 15 is the lowest, and the lowest bit is the purple wire in this braiding, because that was something I made 1 or 2 of these wires and then realized that I had no idea which way the polarity was going. So I introduced just, having one colored wire in each one, and it looks quite pleasing, I think, quite aesthetic. There's generally a pattern to them. So this one's got 3 colors. Well, 2 colors, pink and purple, and then white. So white in this case is the one that I would use to denote the lowest bit. We all have our methods. So here's a pink one, and that is the other half of this byte. So we'll pop that in there. Now, where do the others go? Because it would have made sense if I'd put them all in one line, wouldn't it? The lowest bit of the second byte is going to be on pin 21. And the highest is going to be on 14. So those are here in this header. So lowest is my purple pin, and that's going to be 21. So 20, that's going to be, is that 21? No, that's going to be 20. So this is 21, because we can see here, well, you might not be able to see it. There you go. All of the even pins are on this side, and all of the odd pins are on this side. So 21 is definitely going to be over on this side. So if we say that's 22, so that must be 20, and that's 21. So there we go, 21. And then, again, the other half of that byte, and I can use the long one with the multiple colours for this. So let's assign white as the lowest bit. And again, just pop that in there. Right, so that should be the address bus all hooked up properly. I say properly, I don't know. there's a lot of wire here, so properly might be a stretch. Now, data bus. Data bus. We can use my 8-way cable. Woohoo! And again, it's got one coloured strand in it. And that can go over here. And I know where data bus goes because it always just goes into this analog port. And again, 0 is the lowest. So pop that in. Let's give this a try. Close that, don't need that anymore. Yeah, close that. Close those and make upload. This is how I prefer to use Arduino, to be honest. It's a little bit of an arse trying to find the right parameters to pass to the Arduino command. Yeah, once I've found it, then, you know, I can then just automate this. Well, there you go, that's the command that you use. So it's generally finding this board designator I find a little bit annoying. So I haven't quite figured out the secret to that, but whatever. So let's launch Plum. Hooray! Let's go to memory and help me. Right, what do we have? So let's say we want to write a value. Oh, sorry, memory write. Ah, no, okay, yes, I remember now. That's what the stars denote. The stars denote that they are just control word manipulations, and that's it. So let's just reset everything, and we'll say, yeah, memory poke, which is capital P. Now the address that I want to poke to, let's just say it's 0000, and I'm going to poke a hex 42 into it. Now we can see by this exclamation mark that the data bus is still acquired. So again, we can just release the bus, clear any control word bits, and we can now say memory peak at 0000. And it did not come back with a 42, which is a little bit annoying. Wait, okay, so address select, yeah, and that pulses the 2 clock pins of these 2 registers and ensures that they clock in their data. So, right, okay, that should be fine. Address register out, address bus out. Okay, fine, yeah, because I'm just, so this is the abstraction, so I could switch it over to address register out if I'm using the rest of the, you know, the register modules, but I'm not. So, where was that? Command memory, control word. I have a feeling that I'm not actually asserting the mem in and mem out. Oh, right, okay, yeah. So, peak. Take in a 16-bit hex value from serial. Select that address. Assert mem out low. Yes, because we want to read what's in this address. And then read the bus. And then assert it high because we're not bothered anymore. So, what happened? We were doing the peek and poke, weren't we? Let's have a look at that first. So, let's... Oh, well, that's not going to help, is it? Pulse high? That needs to be pulse low. Okay, let's try that. Cool. Memory. Peak 0000. And we have 0 in there at the moment. Memory, poke, 0000, 42. Okay. Release bus, excellent. Memory, peak, 0000. Ah, damn you. Okay. Kill out of that. And come back to here because evidently... Oh, of course. I could use those. Let's do that. Memory, peak, and let's say 1, 2, 3, 4. Right, okay. Memory. Okay, let's have a quick look at what's on the old pins here. So, okay, off. So, what's it going to be? 4 should be over here. It should be that one, so I would expect that one to be on. And that one is on. Right, okay. So 4, and then on this one, the second nibble, I'd expect 1 and 2 to be on. So 1 is on, 2 is on. Right, okay, so we confirmed that the address is being put into these. Well, okay, let's check this one as well because I didn't actually check that one. So it's going to be 1, 2, 3. So that one's going to be. Oh wait. 4, 3, 2. That's on. And the next bit, got these legs are getting all on. Legs on this LED are getting a bit misshapen, so it's starting to become a bit of an arse pushing. No, you can't really see that, but pushing them in and out. And then the last one should just be 1. And if I can just get that into there, that is on. Excellent. Okay, so yes, confirmed that the memory address is being latched into these registers, these memory address register. So that's fine. What is the state of our output enable? Okay. So write enable and output enable are both high. And if I set, oh sorry, MI, there we go. So I said, please input, which should be write enable, which is, yeah, it is indeed that one. Okay. Write enable has gone low. Cancel that, and then memory output has gone low. That's fine. Nope. Oh, reset. Okay. Oh, I thought I had a help thing installed. No, I don't. Okay. Never mind. How shall I proceed with this? Okay, addresses are definitely being latched in. And how do I'm sure I had a command to read the data bus. Sure I did. Okay, so pin mem out and mem in are definitely included and being set properly. Data bus out, data bus release. I don't have a data bus read. How interesting. Okay, well I can do data bus release using the general reset command here. So let's just take that out and say command data bus in. And I'm going to switch these around because I have a bit of a convention of capital letters being ones that will cause an output and lowercase letters being one that will cause an input. So command data bus in. I've got a databus CPP file, so databus release, databus out, and databus in. Excellent. And do I have a command for maybe in here? Databus out. Okay, so let's just write one here. Void command, databus in. Right. So we're going to want to say, we can just call databus in, that's fine. You int 8t, because it's an unsigned 8-bit integer. I'm not sure what the t means. I'm not a C guy. Read byte is data bus in. Yep, that is correct. Okay, cool. And then we shall say serial print, and then serial hex out, and it will be the read byte, and it should be 2 digits. Do we think that's going to work? Let's find out. Make upload. No! Oh, of course, because I'm not very clever again. I'm typing at a funny angle as well, so it kind of doesn't help. Okay, excellent. Plum. Cool. Now if we say memory out and databus reads 0. Okay, I forgot to put a new line on the end of that, so let's just do that quickly because it's nice and quick. Print line. Let's just full screen that. I'll leave the data sheet open in case I need it again. Cool. Excellent. So what we have, memory peak. I'm going to say peak because this will ensure that we've got a value here in the address register. So 1, 2, 3, 4. Okay, and it says it's 0, 0, which I'm inclined to believe at this point. And then we're going to say memory output. Our read output enable line has gone low, so theoretically whatever's in the chip at this memory location should now be on the bus. And let's just say databus read with a little d. Ooh, that's interesting. Okay. Right, let's just take that off for a moment. It's kind of weak. Not a very bright LED, but yeah, we are indeed getting all Fs. So let's just pop that back in there. So if we say memory poke 1, 2, 3, 4, and we're going to put in 0, 0. Okay. Oh, that's interesting. That stayed on. I should probably ensure that the other counterpart pin is actually in the state that it should be. So, commands. No, it's not in commands H, was it? It was in commands C. It wasn't even there, was it? Come on, learn to type, Daniel. So let's just say digital, right, pin, mem out, high, just to ensure that that is where it's supposed to be. And same here, digital, right, pin, mem in, high, to turn those off. So we make sure that it's only ever in or out. They can't both be in the same state. Should probably write some better code to actually enforce that, but this will do for now. Or it won't. That's also a possibility. Ping memin. Oh dear. No, I can't escape ping. Where on earth did I... Stay with it, Dan. There it is. Try again. Once more with feeling. Cool. Right. Memory help. What have we got? Memory. We're going to peak at 1, 2, 3, 4, and it contains 0, 0. Apparently. I'm not sure that I actually trust that now, but we'll see. So, memory out has turned the output enable signal low, and if I say memory in, it does swap them over. Excellent. And then memory out. Cool. So, little d. Oh, we've got a df. That sounds more like noise, so that could be, well, I say noise. It sounds like a could be an uninitialized value type state. So let's say memory poke 1, 2, 3, 4, and we're going to set it to FF and release everything. Now, memory peak 1, 2, 3, 4. Ooh, came back with FF. Woohoo! I think it is actually working. Just about, tentatively. So, let's say memory peak 4, 3, 2, 1 contains a star, an asterisk, 42. It's interesting. Isn't it just a coincidence that I tried? Because I tried to set one to 42, didn't I? Oh, no. Sorry, that's silly, because this is the decimal representation. This is an ASCII representation. Then we have the binary. Ooh, yeah, I think I may actually finally be onto something with this. So, memory dump. Let's see what happens. Ah, that looks like noise. That looks like a lot of noise. I think it may actually be doing the right thing now. Can break out of that. Let's run the memory test. See what happens. Test. Ah, something crashed. No! What happened? Is it my laptop? No, it's not my laptop. Yeah, okay, fine. What happened? Oh, it only outputs the address if there was a problem with it. So, okay, let's say we're always going to output the address, and sod it. I just want to see some progress. Memory test. Whoa! Okay. It seems to me like it might be working. I know. This might be might make for some better output. AKY. Yep. So let's first well, gonna want those. So before we do anything, let's just output what's already there. address is now going to be write address, or hex in, data bus in. Okay, so that's going to be what's currently in there, and serial print, and then let's just have a colon. So what we'll see is 3 values. We'll see what it was when we first came to the memory address. We'll then see what it read back after the writing zeros, and then what we read back after writing Fs. So we can then say down here, write, read byte, okay. Serial, no, serial hex out, read byte 2, and again here, and let's put that up at the beginning. And okay, this might make for some slightly more interesting output. I just want to see stuff scroll along the screen and make me feel like I know what I'm doing. That was what this project was all about, really. I just wanted lots of flashing lights. Okay. Memory test. Oh, well, I forgot the second colon, but... Oh, that was interesting. Something there wasn't quite what I'd expected it to be. But that said, it did have a reboot, so... well, I say reboot, you know, power cycle. So some of the memory locations may have gone to noise. But it's looking good. I'm just waiting to see a portion of the memory that we haven't already looked at. Oh wow, it's just occurred to me as well that everything at the moment is being powered off the USB port. I forgot to turn on my bench power supply. I'm really not very good at this, am I? Woohoo! Yeah, okay. That's everything. I didn't see any problems in any of that. Let's see if the memory's full of FFs. Indeed it is. Let's try and put in the old memory test routine. This allows me to write characters into the memory locations. So. What? What? Oh, yes, of course. Silly C. Making me declare stuff before I use it. What is this nonsense? Cool. Plum and memory test. Okay. Excellent. Ask. Now, that does appear to have done it, hasn't it? So towards the end, if we see 64, 65, 76, 64, 65, 76, yeah, that does seem to have worked. I think I have an actually working 64K memory module. Hey, who'd have thunk it? Yeah, I apologise for how long and potentially boring this video was. Please leave your comments, and I will attempt to make it a bit better next time. Thank you for joining me, and thanks for watching. Thanks for making it all the way to the end of this video if you are still here. Yeah, have a good one, and I will see you next time.